All right, folks, we are going to now talk about surface area. We discussed arc length, the notion that you have some curve and we want to know what linear distance is represented if you were to move along that curve. Now we're going to take and revisit that issue of maybe a solid of revolution. And then instead of asking about the volume, we're going to ask about the surface area. So much in the same spirit of really any integral, right? We need some geometric object to find area of that we can then sum. And so let's motivate it and kind of think of it, kind of develop it from that perspective and let the geometric needs for representing some surface area drive where we end up. So let me get us on over there. There we go. And okay, so we are talking about surface area. And I'm gonna turn this off real quick here. Okay, so surface area. And we know what that is, right? That's the area over the surface. We've seen it probably in a geometry class or some other experiences, but maybe not in the context of a more interesting type of surface. So how about some motivation here? Here's one of those formulas that you learned way back in the day, and we kind of just put it in our pocket and say either, yeah, I remember what that is, or I don't remember what it is, but I'm gonna go look it up. Well, we're gonna actually find it now, okay? Show that the surface area of a sphere of radius r is 4 pi r squared. So that's something we're actually going to go in and do. So let's back up and start by just thinking about what surface area is and how we might go about actually computing it. So the idea is that we have maybe some piece of a curve, okay? And let's say that we have rotated it, maybe about the x-axis. And so we get this vase-looking thing, or vase, if you will. And let me try to draw at least a little bit better than that, okay? And so the surface area, right, will be just that area occupied by any, well, by its surface, if I could unwrap it somehow. So let's think about what that might be. So if I were to take out a little piece, okay, like maybe I were to just take out this band here, okay? So I'm gonna cut that out and maybe I'll do this. So I'm going to take this band out here and I'm going to move it over here and think about what that actually represents. So if I set it down, it would look something like this. And it has this surface area. Now, geometrically, right, if I consider this as some linear approximation, right, line segments, then what I have is really part, this is a portion of the lateral surface area of a cone. I mean, if I were to extend this up this way and this way, right, I would have a cone shape. And so I've got this piece of a cone, and it's that lateral surface area that I actually want to find. So how do we do that? Well, let's take a little departure here and maybe look at that piece of a cone and what we might be able to determine. So you've got, I'm gonna blow it up a little bit here. So let's say I've got a cone, and let's say I've got a better cone. And we want some piece. Well, notice that we've got some similar triangles here, okay? So perhaps, I'll change colors. And I might call this R1, this R2, and then this hypotenuse L1, and this hypotenuse 2. I could call it L2, but I'm going to call it L just because that's what's represented on this chunk here. And so it's actually part of my surface. Okay, and so then what we're looking for, right, is some expression that would give us this area, okay? Excuse me. So you can see, or it can be shown, that the lateral surface area of a cone is A equals pi r L, okay? A equals pi r L, okay? Now, this frustum, as it's called, of a cone, we want to now try to find the surface area of, okay? And so what we can do is we can look at similar triangles, common technique here. So the similar triangles tell me that L1 over R1 is equal to, well, it's going to be equal to that same ratio for the whole cone, right? Which would be L1 plus L all over R2, okay? So we have on the right side of this equation, we have the big triangle that represents the entire cone, and then the left side of the equation, we've got this smaller triangle from the top to the top of our frustum. Okay, now little algebra from this, and we can show that R2 minus R1 times L1 equals R1L, okay? That's just a little, algebra. Now, going back to my area, right, this guy, we had said in this context, pi R2 L1 plus L, and that would be this whole area, the entire surface area of the cone, minus, if I just want this piece down here, I'm going to subtract pi R1 L1, okay? And so what I can then get is taking advantage of the fact that R1L is this expression. I can then say that area is pi R1L plus R2L. But don't forget what we're actually going to wind up doing, right? We're going to take this and, like anything, right, partition and have these intervals of length delta x. And they're going to become infinitely small. So what does that mean for R1 and R2? Well, how about we just define a new R? Maybe the average. Let's let R be R1 plus R2 all over 2. So that we wind up getting pi R, I'm sorry, 2 pi RL, okay? Because again, right, R1 plus R2 would be 2R, okay? We factor the L out. And so there we go. But let's think again about what's actually going on here. So I think I need to advance a little bit. Well, let me come back. So I kind of ran out of room here. Let me, so I'm gonna get rid of part of this. We have A equals 2 pi RL, okay? So think about what pieces are represented here. We have this 2 pi RL. And what does R come from? Right, R is from the function, right? This is f of x, and the radius, right, is the function. And so if I have 2 pi RL, that R just comes from the function. And so if I'm thinking about these points, maybe this is xi minus 1, yi minus 1, and the second point is xi, yi. Then this 2 pi RL really becomes 2 pi yi minus 1 plus yi all over 2, because remember how we define the radius, right, is just the average of the 2 radii in the frustum. And then L. What is L? Well, isn't L just really the distance between those 2 points? And that should look very familiar, right? If I write it like this, square root this piece here should look like something we've seen before, right? It should look like something we've seen before. So if I want the actual surface area, then I can sum these. All right, taking some sample point. And then this square root we should recognize as being something that we've also seen, right? Namely, in our derivation of arc length. Whoops, sorry guys, I'm having trouble writing. And so this is our approximation. Well, gosh, look what happens if we consider this as a limit of, increase the number of terms we're adding. Becomes this nice formula right here. Okay, well, what do you know? And that's a very clean formula, okay? Sometimes this piece here is called ds, right? If you think about moving along the arc, that's a ds, okay? And so there we have this formula. Now, what I have not done is consider the case where our axis of revolution is vertical, and so you would have, right, 2 pi f of y square root 1 plus f prime of y squared dy. But either way, it's the same idea here. And then again, don't forget the fine print, right? We have a function that is non-negative. The derivative is continuous on the interval. Okay, if we have those conditions, then this formula will hold. Okay, so let's put it to practice here. Whoops, we wanted to show, right, that the surface area of a sphere is 4 pi r squared. So let's start by considering a sphere, okay? And we need to think about how a sphere might be generated from revolving some region. Well, I'm going to pick the function square root r squared minus x squared, right? That's going to be this top half of the circle. And so if I rotate it, then we'll get this sphere. Okay. All right. So we know that the surface area is going to be the integral from negative r to r, 2 pi square root r squared minus x squared, and then square root 1 plus, and then the derivative squared. So if we go in and find the derivative, right, f of x is the square root r squared minus x squared, f prime of x, well, chain rule, right, we'll have a negative 2x as the derivative of what's inside my radical. And that radical is to the 1/2 power, so my derivative will wind up being negative x over square root r squared minus x squared. dx. Okay. All right. So let's start playing around with this thing here. So we have 2 pi negative r to r square root r squared minus x squared. And then let's see what happens to this other one here. You get 1 plus x squared over r squared minus x squared dx. Which is 2 pi, negative r to r, and then what are we gonna get for this second square root? Well, my common denominator is r squared minus x squared. And so we'll have r squared minus x squared plus x squared. So my numerator is r squared, my denominator r squared minus x squared dx. And look at how nice things wind up. This is 2 pi negative r to r. Well, r dx. And so we're going to get 2 pi r x from negative r to r. Just 2 pi r times r minus negative r, which is 2r. And so we get 4 pi r squared, just as we were supposed to. Okay? All right. So that's, well, let me turn my video on. So that's how you find the surface area. Again, it comes from this notion of revolving some region to create this three-dimensional object, a solid. And then we're taking those frustrums, which are just portions of a cone, and using those as our surface areas that become summed and therefore lead us to, no surprise, the integral, okay? Also worth noting that I don't want to say sides, but the pieces of the cone, right, that portion of the cone that becomes our surface area, the lateral sides there are actually arc lengths, right? And so we also shouldn't be surprised that the arc length shows up in our formula for surface area, okay? Now we're going to revisit these topics again. We're going to see arc length and we're going to see surface area again when we look at solids and functions from a polar perspective. When we look at polar coordinates, and parametrizations, we're going to see these again. And so you want to keep these formulas in the back of your mind so that we can really reconcile what we see they are from this perspective with what they'll be under some parametrization or in an entirely different coordinate system, such as polar coordinates. All right, so that's surface area. Now it's time to practice, which is what we'll do next.